All right, welcome back to the lab lecture video series. This week you're going to be performing experiment C, which is using absorption spectroscopy to determine concentration. And based on the look on this guy's face, you can tell that this is going to be a really fun experiment. In fact, he might even say that this is going to be utterly fantastic. All right, moving on from that. Let's think about this process of absorption and emission of light by electrons that we talked about with our emission experiment. In particular, we said that electrons can be excited from a lower to a higher energy level when they absorb energy. And that energy can be applied via something like electromagnetic radiation. Those electrons then want to relax back to a lower energy level, and to do that, they have to give off energy. Sometimes that's in the form of visible light. And with emission spectroscopy, we were looking at that light that's given off as the electron relaxed back down. Now, emission spectroscopy, as you might have noticed, is used typically for colorless solutions. All the solutions we used in experiment B were colorless. And we used this to identify metal contaminants that were present in solution. We were able to say, based on the emission signals, this is in solution, or this is in solution, or this is in solution. But one of the things we didn't do was quantify the amount of those metal contaminants in solution. This week, we're going to be looking at the other side of this process, namely the absorption of energy as an electron is promoted from a lower energy level up to a higher energy level. In this process, we're looking at that light absorbed and recording the amount of absorption of light and using that to figure out exactly how much metal contaminant is in a solution, the concentration of that metal contaminant in solution. Now, this is typically used for colored solutions, and if you think about that for a second, it makes sense. Colored solutions are colored because they absorb wavelengths of visible light, and the ones that they don't absorb are reflected back to us. That's the color we interpret something to be. And so that's why we use this technique, absorption spectroscopy, typically for colored solutions. But we're going to be looking at this absorption of energy by electrons as they're excited. So how do we actually take measurements in this process? Well, we use a light source that can provide electromagnetic radiation, and we apply that radiation to a sample that is held in a sample container called a cuvette. And then light that is absorbed by the electrons causes less light to reach the detector than what originally left the light source. So we have less than 100% of the light that's transmitted through the sample. So we'll have less than 100% transmittance. Now wait a second, didn't I just say we were talking about absorbance and not transmittance? So how are those two related? Well, if something absorbs more light in the sample, then less will be transmitted. In fact, the absorbance is equal to the log of 1 over the transmittance, so they're very closely related. Absorbance is directly proportional to concentration, and this is the reason that we can use absorption spectroscopy to determine the concentration of a solution. If you imagine a solution, and let's say we could actually visualize individual absorbing species. Let's say these are metal ions in solution, right? If each species here absorbs a photon of light of appropriate wavelength that corresponds to an electron's transition, then the more species we have in that same volume of solution, the more photons of light will absorb. And the more light that we absorb, the less light will be transmitted through the sample. So the less light will reach the detector. In this way, more concentrated solutions will absorb more light, and less light will reach the detector. And again, a reminder that the light has to correspond to an energy that matches an electron transition in that particular absorbing species. And we know that that energy corresponds to a particular wavelength of electromagnetic radiation. Okay, so back to our basic experimental setup where we have a light source, a detector, and a sample in between. Right? The more light that the sample absorbs, the less reaches the detector. Therefore, more concentrated solutions will allow less light to reach the detector. Great. And in theory, this is fine, but this is overly simplified. In fact, there's some problems that we need to deal with in this kind of setup. One of those is that light is caused to go other directions than the detector for other reasons besides absorption. There are other reasons that light, that's a better way to say it. There are other reasons that light does not reach the detector besides being absorbed by the sample, namely reflection, refraction, and diffraction. Basically, as the light travels through the solution and the cuvette itself, it gets scattered. And that causes some of the light to not reach the detector, not because it's absorbed, but just because it's scattered in different directions. This causes a problem because based on what the detector is seeing relative to how much light left the light source, the detector interprets that as, well, more light's being absorbed, meaning it's thinking the solution is more concentrated than it actually is. So that can lead to errors. So we need to be able to kind of account for this diffraction, refraction, and reflection, right? How do we do that? Well, we can use something called a blank or a reference cuvette. Now, a blank or a reference cuvette, it typically contains everything that's in the sample cuvette except the absorbing species. It's as close as you can get to what the actual solution is. Same cuvette, same solvent, and sometimes other things that are in solution besides that absorbing species that you're interested in. And that reference cuvette, since it still has a solvent in it and it still has the cuvette that you're going to be using for your samples, will cause light to diffract, to reflect, and refract, basically scatter and go other directions just like the sample will. So we can take an apparent absorbance reading from our blank or reference and get a kind of a baseline for how much light should be reaching the detector if the solution does not contain the absorbing species, just has that diffraction, refraction, reflection. Then we compare that to an actual sample. We can subtract that out from a sample. So we take the apparent absorbance of a sample cuvette, and we subtract from that the apparent absorbance of a reference or blank cuvette, and that gives us the absorbance of just the species of interest that's in solution. And so here we've got what's called a dual beam spectrophotometer. This is kind of a higher grade model than what we're going to be working with. It will actually take simultaneous readings of the blank and sample and do this subtraction for you all at once. You're going to have to do this in sequence. So you'll first put in a reference or a blank, take a reading, and then you'll put in your sample, take a reading, and the spectrophotometer you're using will do the subtraction then. You just can't measure them both at the same time, just in sequence instead. Okay, so what is an output when you take an absorbance reading from a sample? What does it look like? Well, that produces an absorbance spectrum, which you can tell is absorbance versus wavelength. Now, unlike our emission spectrum that you saw in our previous experiment, we don't have these sharp, narrow peaks. And in fact, we have this very broad peak here. And these broad peaks in absorbance spectra are called absorbance bands. Now, this is a sample absorbance spectrum of a copper-2 complex. Notice there's only a single absorbance band for this particular complex. For other species in solution, they may have multiple absorbance bands. This particular one only has one, and you're going to be looking at copper-2 in your experiment this week. So this is what you expect to see with a band in a very similar or same location, actually the same location because you're looking at the copper-2 sulfate, and this is an example of a copper-2 sulfate solution. Some points I want to make about this particular absorbance spectrum. One, there's a little bit of noise at the top here, which is not ideal. Usually you want a nice smooth peak because noise can cause problems. So you want to avoid noise. This one has a little bit more than maybe we would like, but in your most concentrated solution, you might see a little bit of this, but try to avoid that. But the things I really want to highlight are the things called, one, the lambda max. The lambda max is the wavelength right here, so about whatever this is, 770 or so. It's the wavelength at which maximum absorbance occurs. It's the wavelength at which the maximum of the absorbance band occurs. And so that wavelength here is about 801.54 nanometers. And the absorbance at that point, 1.145 in this case, is my absorbance that I would record at that lambda max. So the lambda max, again, wavelength at which the maximum absorbance the wavelength at which the maximum absorbance occurs, and that is the wavelength at which you want to record all of your absorbance values for the entire experiment. Once you have identified the lambda max, here I'd say it's about 801.54. Yeah, sure, somebody else looking at this might say, well, I think it's about 803.96. Whatever you determine it to be, once you've picked it, stick with that throughout the entire experiment. That is absolutely key. All absorbance readings must be made from the same lambda max value. Once you determine that, that's where you're going to record your absorbances. If my absorbance was at the lambda max of 801.54, my absorbance reading I would record would be 1.145. So for each sample that you run, you're going to get an absorbance spectrum that looks like this. Depending on how concentrated the sample is, this absorbance band may be higher or lower. It'll get lower as the sample is less concentrated, and it's more intense as the sample is more concentrated. But for each sample, you'll get an absorbance spectrum like this. Okay, so now we know what it looks like when we run an absorbance spectrum. We know what the data kind of appears, how that appears. But how are we going to use this to determine the absorbance of a sample for which the concentration is unknown? All right, we already established a very basic relationship between absorbance and concentration. The more concentrated a sample is, the more absorbing species in a certain amount of solution, and the more light that will be absorbed. Great. But there's more to it than just that. There are two other factors that we have to consider that will affect the absorbance. One of those is called the molar absorptivity coefficient. The molar absorptivity coefficient is a factor that takes into account the fact that different species are inherently different and will therefore absorb different amounts of light because they're different species. And so each species has its own absorptivity coefficient that is unique to it. And the other factor that can affect absorbance is called path length. Even if we have the same absorbing species in solution and the solutions are the same concentration, if the light has to pass through more solution before it exits, then more light will be absorbed. It will encounter more absorbing species and more light will be absorbed. So the path length also affects absorption. These three factors taken together give us this mathematical relationship which is known as Beer-Lambert's law, or often just shortened to Beer's law. But don't do that because Lambert deserves some credit too. All right, so Beer-Lambert's law. Absorbance is equal to the molar absorptivity coefficient times the path length times the concentration. How do we use this relationship to determine the concentration of an unknown? Well, absorbance is something we can measure, right? We find the lambda max. The absorbance at that lambda max is our absorbance for a given solution. Okay, the molar absorptivity, well, we don't know that. And the path length, we don't initially know that. And we want to find the concentration. We got three unknowns here. One we can measure, and then three unknowns. Man, that's tough. So what could we do? Well, we could take a solution for which we know the concentration, make a solution for which the concentration is known, right? Then we know C, we can measure absorbance, and the path length is something we can actually measure as well, right? All you need is something like a ruler that can measure the distance that the light's traveling through the sample. So that can actually be measured pretty well. And so if you know the concentration, you measure the path length, you measure the absorbance, we can determine the molar absorptivity for a given absorbing species. Once we know that, then you can go back, right? You can take a sample of unknown concentration. You know its molar absorptivity, as long as it's the same absorbing species that you did this on in the previous couple slides, and you can measure the path length and you can measure its absorbance. That means you can determine its concentration. Fantastic! So we can determine a concentration for a solution for which it's unknown using absorption spectroscopy. However, our determination of that concentration in this case is based off of a molar absorptivity we determined from one solution, which is not going to be the most accurate way to do this. So how can we do this in a process that's a bit more accurate? All right, glad you asked. Well, what if we measured absorbance values for not just one solution of known concentration, but for several solutions of which the concentration is known? And let's say that we keep the cuvette that we're using to measure that solution the same throughout. Then the path length will remain constant because it's the same container containing that solution. Since it's the same absorbing species, just differing in concentration, but not identity of what's in solution, the molar absorptivity would be a constant as well. So both the path length and the molar absorptivity are constants, and two constants multiplied together is still a constant, just a bigger constant. So that means that absorbance then would be equal to a constant times the concentration. Now, if you're looking at that and saying that looks kind of like a familiar mathematical relationship, well, that's because it's the form of a line, y equals mx plus b, where b is 0. Y is our absorbance, the slope would be our constant, and x is our concentration. This provides a very, very useful linear relationship between absorbance and concentration that we can exploit. So, let's say that we take a set of standard solutions, solutions for which we know the concentration. And for each of those solutions, we record an absorbance at the same lambda max, right? Again, each solution we take an absorbance reading of will look like this, but the absorbance band will get smaller and smaller as the concentration goes down. So that absorbance reading at that lambda max will also decrease, right? The top of that peak will go down. So we take absorbance readings for the different solutions of known concentration. That gives us a set of data of absorbance versus concentration, which we can plot, and will give us a linear relationship. So here are each of those data points. A1, C1 would be like, one of these, A2, C2, A3, C3, depending on whether I'm getting more concentrated or less concentrated, but it's these data points plotted. And then I can do a linear fit to that data because it's a linear relationship between the absorbance and the concentration. Okay, great. I have taken a set of known solutions of known concentration, I've determined their absorbances. How does this help me get the concentration of a solution for which I don't know it? All right, well, again, here's our sample Beer-Lambert plot, which, by the way, that's what the linear relationship between absorbance and concentration when plotted, that's what it's called, the Beer-Lambert plot. And whenever you make your Beer-Lambert plot, which you will, make sure you include the lambda max value that you used in your title. Okay, I didn't do that here because it's a sample plot, and I really should have, but make sure you include that. All right, so back to this. We have our linear fit, and with that linear fit, we can get a nice equation that goes with that, and we can do all that with Excel. And if you're having problems with Excel, I made a short video where I actually demonstrate how to graph something in Excel. So hopefully that'll help out a little bit. I can't remember if I did the Beer-Lambert plot or not. But I probably just showed how to graph absorbance. But maybe I did. Anyway, if you need help with graphing in Excel, come talk to me. Okay, or a TA. Anybody can help you with this. All right, so we get this linear relationship. But I've got a solution for which I want to find out the concentration. How do I do that? Well, let's say I take that solution and I take an absorbance reading. And at the same lambda max I used for all of these, I find that the absorbance is 0.680. Now, the very not accurate way to do this, the very rough way to do this would be say, okay, well, this having the same path length, if I'm using the same cuvette, and it's the same absorbing species, so same molar absorptivity, will fit into this linear relationship as well. So the absorbance of 0.68, I'm going to come about right here and go across. Oh, that's about here, and then I come down, which is about 0.062 or 3. So the concentration should be 0.06 something. Now, how do I do that more accurately? Well, I just take the equation from the actual line itself, right? And that's y equals 10.41 plus 0.0211. Again, you get that from Excel. And I plug in my absorbance for y and solve for my concentration x. So let's put in our absorbance of y at 0.680, solve for my concentration of x, and x comes out to 0.0632 molar. And that's how we're going to take a solution of unknown concentration and figure out what it is using absorption spectroscopy. So here's an overview of the experiment. First, you're going to need to make a set of standard solutions, solutions for which the concentrations are known. I'll talk a little bit more about that in a minute, and your TA will also give you instruction about that at the beginning of lab. Once you've made those set of standard solutions, you're going to take absorbance readings of each of those. You're going to determine what the lambda max is and use that same lambda max for every solution throughout the experiment. And at that lambda max, you're going to record an absorbance reading for each of those standard solutions. That gives you a table of data of absorbance versus concentration, which we can use to make our Beer-Lambert plot. Again, include the lambda max that you used. All right, that Beer-Lambert plot, we can include a y or a linear fit equation. That linear fit equation we can then use with the absorbance of an unknown solution, plug in for y to solve for x, and we get our concentration. All right, so how are you going to make these solutions of known concentration? Well, first you're going to use a couple different pieces of glassware that you haven't seen before. One is a volumetric flask. We're going to give you some 10 ml volumetric flasks. And you're also going to be using a graduated pipette. Your TA will go over how to use both of these at the start of the lab to give you a kind of an idea, but if you want to go ahead and Google, using volumetric flasks or using graduated pipettes, you can do that so that you're even more prepared. But your TA will go over that at the beginning of the lab. One of the things I do want to mention with the volumetric flask, though, this is a piece of glassware used for making a specific volume of solution and that volume only. That's why there's one graduation on it. This one would be a 500 mils, so it'd make 500 mils of solution, but we're going to give you 10 mil ones. So you'll be making 10 mils of solution at a time. How do you use that to create a solution of known concentration? First, we're going to give you a solution that is pre-made of a set concentration. It's going to be 0.1 molar copper 2 sulfate. So that can act as one of your standard solutions. So you actually only have to make 4 more. You can take that and take a little bit of that concentrated solution and add it to more solvent, water, to create a more dilute solution. Exactly what that new concentration is will depend on how much solvent you add to how much of that original concentrated solution. So you're going to take a little bit of that concentrated solution and you're going to add that to some water. So the right way to do this is to put actually quite a bit of solvent into your volumetric flask. Remember, volumetric flask right here, right? So you put some water in here, and each one of these cylinders represents a volumetric flask. It's just easier to draw. So put some water in there. Okay, then you're going to add a set amount of the more concentrated solution, and then you're going to add more water up to the line on the volumetric flask's neck. Then you know the total volume of the new solution that you've created. And this equation that you can use to calculate the volume or the concentration of this new solution is M1V1 equals M2V2, or C1V1 equals C2V2. C1 stands for concentration, M1 would be molarity, but you can use it for any units of concentration. So we take our starting solution concentration, let's say it was 0.1 molar, and let's say that we removed 2 milliliters of that 0.1 molar solution and added it to enough water to create a new solution that is 10 milliliters. Right? So I would take I'll grab my calculator here for you. Let's say we took our 0.1 molar solution and we took 2 mils of that, so 0.1 times 2, and then we're going to divide that by the volume of the solution that we made to solve for C2. And we made a 10 mil solution, so we divide by 10, and so that new solution would have a concentration of 0.02 molar. Now we've got a video that talks a brief introduction to concentration that you should be watching in addition to this lecture video, so make sure you've watched that because it'll give you additional help with this. In any case, you're going to make 5 standard solutions. Well, you've got 1 to start, so you only have to make 4 other ones. And you can make 5 standard solutions for which the concentration is known, although you have to be careful, right? Your technique in making these solutions will determine how accurately you know their concentration, which will ultimately determine how accurately you can determine the unknown concentration. But you'll make your 5 standard solutions, go through that process we already talked about, and you'll be able to determine the concentration of your unknown solution. Some overall reminders for this: we will be using gloves for this experiment. Copper 2 sulfate solutions are not that particularly bad, but it is somewhat toxic, and because of the use of new techniques and graduated pipettes, there's a higher risk of contacting the solution, so we are going to use gloves for this experiment. When you're using gloves, make sure that you're not handling personal items. Anytime you spill something on the gloves, immediately change them out for new ones. Removing gloves. Your TA will show you how to properly remove gloves at the beginning of lab. If not, ask them to do so. There's a special way to do that. But remember not to handle personal items with gloves on. It's not for writing in your lab manual. It's not for using your calculator. Gloves are when you're handling chemicals. When you're not handling chemicals, remove them and don't be handling your personal items, pencils, etc. with those on. And then, as always, don't have any cell phones or anything out in the lab. Again, more accurately you do your dilutions, the more accurately you'll be able to determine the unknown concentration. Make sure you know what concentrations you'll make and how you're going to make them before you come into lab. It'll save you so much time. Your most concentrated solution will be a 0.1 molar copper 2 sulfate solution, right? You know what you're starting with. Your least concentrated solution should be 0.01 molar. Okay, so you know what your most concentrated and least concentrated is. You can determine what the ones are in between, but try to space them out evenly. Go ahead and plan out what solutions you're going to make and how you're going to make those. Then, reminder that you should turn in all plots with your lab report properly labeled, titles, axis, titles, units. I already talked about with the Beer-Lambert plot, including the lambda max value. Make sure you do that. As always, make sure you're washing your hands when you're done with lab for the day. And of course, make sure you're having fun in lab. If you have any questions, ask myself or the TA, and we'll be happy to help you out.